method of joints. So when the truss is in equilibrium, right, the logic behind this method is that at every joint there should be equilibrium. You have a big structure, different members connected with joints. If you look at every, as we said, when we have something in equilibrium, every part of that structure or body is in equilibrium. The same story about joints. If we have a truss that is in equilibrium, then each of its joints is also in equilibrium. And that's what we're going to use to study, or that's the ingredient of method of joints. So let me just write it here. If a truss I can write it there, truss. If a truss, I forgot what I wanted to say. If a truss, all right, is in equilibrium, hopefully that's what I wanted to say, equilibrium, each joint is also in equilibrium. So for each joint, we can just pretty much write summation of forces in x direction should be equal to 0, and summation of forces in y direction should be equal to 0. This is very similar to what we were doing for a particle in a two-dimensional space. Now, that particle would be the joint. What are the forces applied to that particle? Are the combination of all the forces in that joint. Now, those could be external forces and internal forces. External forces are the forces applied to the structure, to truss at those joints. Well, the truss has no force applied to it on the member. Forces are always applied to the joints. So there are some external forces, depending on what type of truss we're looking at. And internal forces, if we draw the free body diagram for just that specific joint. Let's just go through this with an example. Right? Things make more sense if you look at an example. So let's say we have this structure, a simple truss. I'm going to bring it here. There you go. This is a truss. We have 3 members there. It's pinned at point A. It's a pin connection at point C. It's a kind of a roller. And we have an external force 500 newtons applied to point B, joint B to the right horizontally. And we are asked to, what is the problem statement? It says determine the forces in each member. Determine the forces in each member of the truss what else? And whether the member is under tension or compression. So 2 things we are asked to find. Just kind of you have to find the members. You're going to figure out if the members are in tension or compression, even if you're not asked to anyway. But in this case, you're asked to specify clearly. Now, I have to give you a couple of rule of thumbs, 2 rule of thumbs that are going to help you when you want to use method of joints. The first question would be, well, that's the approach. We focus on one joint. We isolate that joint. We draw the free body diagram for that joint. Now, free body diagram for each joint includes external forces applied to that joint and internal forces. But the first question would be where to start. Which joint should I start? Usually that can determine, it can make your life easier or a little harder. And the other thing is that about the direction of the forces. But let's just go one by one. The first, maybe, I'm going to add this here. We draw free body diagram for joints and use summation of forces equal to 0 to find the unknown internal and external forces. But the question would be where to start. Right? I'm going to give you two rule of thumb. I would say I'll put it under notes. Note. I'll write this with a different color. I have, I don't know which color. I'll just keep it blue and I'll separate them from the rest. So the first note would be when using the method of joints, always start from let's put this, start from a joint that you have at least one known force and at most two unknown forces. Very important. Right? You have to deal with this a lot. Deciding where to start. That is going to help you where to start. So when you look at it, truss, you want to decide where to start. You start from a joint that you have at least one known force and at most two unknown forces. You should not have more than two unknown forces, and you should have at least one known force. Keep that in mind. And also the other note is about the direction. So when you draw the free body diagram, let's say in this case, you want to draw the free body diagram for this specific joint, joint B. You want to isolate that and look at the free body diagram. One decision you have to make, let me take it here. And let's say this is point B. Right? I'm drawing the free body diagram for point B, for joint B. Joint B. Well, I know there is an external force applied to it this way. Right, going back there, point B is 500 Newton. If I take it out, each of those members, I should replace them with two internal forces along the member, right? Remember, these are two force members, so any internal force that you put is applied to that joint at that specific place is along the member. So we know the line of action. Now the question is, how do we know the direction? Should I put these this way? Like, should I put it like this? One for the member, vertical member, and one for the member in, what is that member? BC. Should I put them this way, facing the points? If I, again, if I replace those in that free body diagram, if I want to put the internal forces, or should I put it this way? Or maybe I should just put it this way. So there are different possibilities, right? Depending on, I know the line of action. The line of action should be aligned the member, because these are two force members. This is a truss. All members are two force members, and the internal forces are along the member. Now, how do we figure out the direction? Right? This is 500 newtons. You already know that. Let's put it here. 500 newtons external force, and this is joint B. Now, the direction of the force in a member with an unknown force, right? In this case, these two internal forces are unknown. In so many cases, you actually have to, believe it or not, you have to figure that out by inspection. What do I mean by inspection? When you look at this structure there, 500 Newton is pulling it this way. If you think about the free body diagram of the whole structure, what do we have? This is a roller, so it's just one force vertical. Remember the supports in 2-dimensional. This is a pin. I don't know the direction of these forces. But one thing I know, this structure is not moving, right? So when it's pulled this way, what is your guess about this member? Is it under tension or compression? How do you see it if you want to imagine that, well, this is being pulled point B, or the part B of this truss is pulled by 500 Newton to the right. And this is fixed. Point C is fixed. Point B is also fixed. I have a member like this. Good guess. Yeah, it's under compression. But let's see if most of us can see it. So this is the member, tilted member, right? It's on the ground like this. I'm applying this force this way, right? 500 Newton. If you have a pen or something around you, you can think about that, and you can like mimic what I'm doing here, copy what I'm doing here. You can feel the pressure in your hand, right? This wants to go inside. When you apply this force this way and want to keep it horizontal, this wants to go inside. Well, it's not going inside, obviously. So this member is under compression. Member AB, right? If you have it this way, right? And if you're pulling it in this direction, this is a little harder to see. So think about it. You only have two options, either tension or compression. Nothing else can be force, internal force in a member of a truss. So if I pull it this way, this member wants to elongate. Right? So when I go this way, it wants to elongate so it can actually, well, this is fixed. It can actually continue or go along with this horizontal force. Elongating, or the tendency to elongate, for the tendency it has to elongate, it means it's under compression, it's under tension. So if this member is under compression, let's go to member, take a look at, keep looking at member BC, right? It's under compression. If it's under compression, these two forces on both sides are trying to compress this. Now, I'm looking at joint B, not the member BC, which means that I have to put the opposite force, same magnitude at joint B. This one is under compression. Right? Think about the spring. When it's under compression, the spring is trying to push your hand back, or push whatever is trying to compress it back. So the force on point B should be in this direction, coming from member BC. Call this FBC. Now, if you agree that AB is under tension, again, two options. Go back to these two members under tension. If it's under tension, again, think about the spring under tension. When you're pulling it from both sides, the spring is trying to go back or pull your hand back to where it was, right? The tendency it has. So If it's under tension, it means Newton's third law tells us, well, if those forces are in this way, the opposite direction should be on the other part. So if I take this point B out and look at this just point B, this should be downward, because the member connected to this point, to joint B, member AB in this direction, is under tension. So F, call this BA. So like it or not, so many cases you're going to end up using inspection to figure out whether this member is under compression or tension. Now, there are and I should add this, that we'll go over this in a couple of examples. If you get one of them right, if you get FBC right in this case, and you can't figure out what FBA is, that is fine, because eventually you're going to get a negative value for FBA. So if I got FBC right, and I figured out, oh, it's under this member BC is under compression, so FBC is in this way. But I couldn't figure out the direction of force for member BA. Let's say I just put it this way. I do not understand this under tension. I thought this is still under compression too. This is also under compression. That is fine. If you get one of them right, the other one, you're going to end up finding it as a negative value, which tells you that in your free body diagram, you should have flipped it, meaning that that member was under tension. Try to get them right, but it's not always possible. Just one of them, get one of them right, you're good to go. Now, from here, the rest is just free body diagram of a point in two-dimensional space. As long as you know the angles, well, this angle, what is this angle? Can someone tell me what this angle is? Theta.
Would it be 45 too?
It's 45, exactly, right? This is 45, so this is 45 degrees, and this is 90, so right triangle. So, go there, and put here 45. The rest again is like exactly what we used to do for when we were doing for free body diagram or equilibrium of a particle in two-dimensional space. Summation of forces is equal along x is equal to 0. Let's take this as positive. Let me use the color I usually use for solutions. And x is equal to 0 in this direction is positive. That will give me 500 minus FBC sine 45, and that's pretty much it, is equal to 0. So I can find FBC. That would be, double check. Yes, it would be 707.1 Newton. So I found FBC. Force, internal force in member BC. Summation of forces in y direction is equal to 0. So minus FBA, right? Well, it's y direction. So let me be more clear. This is the positive direction, and this is the positive direction. So minus FBA plus FBC sine 45 degrees is equal to 0. So we'll find from there FBA becomes FBC sine 45. So whatever, actually cosine 45. Why did I put sine? Looking at it, this is 45. Well, also, it doesn't matter since sine and cosine for 45 are the same, but let's be correct because the other angle is also 45. That would be FBC cosine 45 becomes 500. No, that would be your FBA. Now, we found the internal forces in member BC and BA. only one member is left, AC. We are asked to find the forces in each member. Now we know what is FBC, we know what is FBA, we want to know what is FAC. So to find FAC, I either can go to joint A or can go to joint C. Keep in mind that note, when using the method of joints, always start from a joint or use a joint, maybe not even a start, use a joint that you have at least one known force and at most two unknown forces. So at point A, I have two unknown forces. Right? Point A is a pin connection. So I have two unknown forces from the ground and another unknown force from AC. Let me draw the free body diagram for this. Isolate this, take it here. Let's see what we have there. At point A, I have AX, or AY better to say. This is AX. I have FBC, which I don't know what it is. And I have from BA, right? We said BA is, remember, that it's BA is under tension. So the direction of the force on BA would be this way. Now the problem with this is that if I want to go with A and find FBC, I don't know, well, I still can do that. I know AX and I know AY, right? So I can just use this. I have two unknowns. Well, I have three unknowns, so I can't use that, sorry. I don't know what FBC is, I don't know what AX is, and I don't know what AY is. We said we should have at least, at most, two unknown forces. So A is not going to work for me. Let's take a look at joint C, right, and isolate this. If I isolate that, let me write here, free body diagram for joint C. And let's put it here. Now on joint C, well, from the ground, this is support force, upward. Wouldn't that be FCA and not FBC? FCA, exactly. Yeah, well, I don't know why they put F. Thank you. That would be F along the member C, CA or AC. Right? So we have too many unknowns for joint A. For joint C, I have one force from the ground, right, this way. Let's call this CY, I would say, or let's call this FC to be consistent. But that's the support force, right, from the ground. It's a roller. I have two forces, other forces in that joint. If I isolate that, I look at that specific particle free body diagram, those internal forces from the members, you can think about them now. External forces apply to that specific joint. They're coming from members. I know their directions. The magnitude and direction for that one, I know. This one there, it's this way, right? That member is under compression, so it's pushing this point. It's trying to expand itself since it's under compression. So this would be FBC. And we have one force along AC. Now, in this case, I can't really even figure that out. I don't know what's the direction. It's not that easy to guess. You might guess, but I'm going to go with the fact that I don't know. As I said, we can have one unknown direction in each joint. Previous one, we figured out BC is under compression. I said BA, if you can't figure it out, don't worry. Just put it in one direction and you'll get a negative value. Now, in this case, I don't know. I'm going to assume that I don't know the direction. So I'm just going to put it this way. These two I know. Remember, FBC I know and FC I know. The only force you can afford not knowing one direction for each joint. That would be FCA. The angle was 45, so I'll just put it here. Now we'll just do what we were doing for this member. Let's do it this way, and then summation of forces in X is equal to 0. I'm going to take this as positive. would be FCA plus FBC cosine 45 degrees. And that's pretty much it along x is equal to 0. So from there, you can find, let me put it down here. You can find FCA as minus FBC cosine 45, which would be 500. So this becomes minus 500 newtons. Now this turned out to be negative. This means, just going to write it here. It should be in opposite direction on free body diagram, meaning that the direction wasn't correct because I got negative. Now, if the direction is flipped, can someone tell me whether this member is under compression or tension, FCA? That's something that you needs practice. So now FCA is in this way, right? FCA becomes this way. Exactly, it's under tension. Because when you flip this, well, you have the force in this direction. The opposite of that is on your member. Think about it this way. If you flip that force, then on AC member, you're going to have, let me draw it here. Member AC, we're going to have this set of forces would be FAC, FAC. Thank you, guys. Yes, it's under tension. So summation of forces in y direction is equal to 0. Upward is positive. We go there. It's going to be FC minus FBC sine 45 degrees is equal to 0. From there, you can find FC as, again, 500 newtons. So the direction, well, we know the direction is that way since the other one is compression. All right, so I already draw AC member. We said it's under tension. We figured that out at the end. And we figured other ones out when we were talking. We said BC is under compression. So I'm going to draw BC here. Let's draw it like a normal line. This would be BC. This is point B. This is point C. And we said it's under compression. So the forces would be like that. Compression. And the last one would be AC. I'm going to fit it here. I know it's a little squished here, but squeeze there. BA, and that's under tension. So the forces on the member are going to be like this, tension. All right, that's all we wanted to find out. So let me say these are together, and these are members. I was trying to separate them, but apparently didn't do a good job. These are just wanted to mention that what is the state of each member, which we were asked, is under tension or compression.